Thank you, Paul. So thanks everyone coming to this QMCPACK school, and I'm very proud to show you our recent year effort on the GPU support. So I'm Yilov, a computational scientist from Argonne National Lab. I work on all those leadership computing machines, like the supercomputer in Argonne, and through the QMCPACK project, I use all the machines across the country. So, okay. So this is a high-level intro, just to give you an idea of what I'm going to take care of the whole presentation. So I will first give you a quick intro. The QMCPACK basically, so far I believe I'm very confident it's a flagship high-performance. It has high-performance GPU acceleration support, and I'm doing my best to make it being the flagship code in the QMC community. So far we have all the vendors supported, all the GPU vendors, and the current implementation we give you is a feature complete implementation. Even you are using GPU, and you always have all the QMC features available at run. So we made recent year we made change to make it easy to build when using GPUs. You could find all the details about all these image configuration options in the menu. We have example build script in the common folder. In our folder for common supercomputers, you could figure it out. But overall, it's really simple to build. And QMCPACK is also very easy to run regarding GPUs. You almost don't need to make any change in input files. And for performance reason, we only recommend a very minimum fine-tuning effort. So in addition, we are very happy to help support new machines as users may encounter issues, and we exchange our experience, help users through all the GitHub issues and also through the QMCPACK Google group. So a very brief history. So QMCPACK actually evolved its GPU implementation in multiple stages. I would say the initial GPU support was only for NVIDIA GPUs, was introduced by Ken Esler in 2010. It's CUDA only. It served us very well for many years, but eventually, because we are trying to expand its capability, we need to update the design, expand support for different vendors. We kind of created a new implementation. So right now, the only implementation kept in current QMCPACK releases, like 4.0, 4.1, that's the performance portable implementation. It was supported by Exascale Computing Project. Right now, it works across all the major GPU vendors. And we used OpenMP Target as the portable programming model for a lot of places so that we don't need to repeat the implementation for different vendors. And thanks to all the design choices, we have CPU fallback. If a feature doesn't work on the GPU, you can mix and match features, CPU features, GPU features in QMCPACK. So this allows you to run your simulation, get acceleration, and also get the intended calculation, the feature being used. So for more details about this implementation, you can look at my paper. So published in 2022, that's the link. Okay, just give you an idea what's the status of the QMCPACK GPU support in terms of performance. So this is a study, I think it's a snapshot of the performance for since April, I believe. Yeah, so it's quite recent. And so far, we've enabled the performance on all the major vendors in very decent speed up you can see on the figure. So on the right side, the figure is the speed up. So The black solid line is 1.0, means that's the reference CPU on LCF Polaris machine. And on Polaris, we have the A100 GPUs. That's why with GPU acceleration, the green bar, you see a factor of 5 around that number speed up compared to using only the CPU on the node. And then you can see that I'm also showing you the Frontier numbers and all the Aurora numbers. I would say they are all very decent performances. And over time, we're gonna further improve it, but that's already a very good status, how to say, performance for you to run production simulations as of today. So you should not worry about or scared about using the GPU code if GPU is around you. I mean, okay. So hardware we support so I'm giving you a bit more details. For all these vendors, we not only support the cutting edge, the highest performance card, GPU card, which usually is categorized as data center GPUs. We actually support almost all the GPU variants that the vendor provides, as long as their software supports it. So you can have workstation GPUs, I say desktop GPUs, or you can think of them as gaming GPUs. There are also laptop GPUs, and laptop GPUs are not constrained to just discrete GPUs. There are also integrated GPUs. We can run them on. For example, I have both an AMD laptop. It has a like APU stuff. I can run the QMC simulation on its GPU part. And similarly, on my other Intel Lunar Lake laptop with the Lunar Lake CPU, I can run the simulation on the integrated GPU of that machine. Yes, they are not powerful, but it's very easy to use, very accessible. Even they're not intended for you to run heroic simulations, but you can kind of quickly troubleshooting stuff or investigating small things very easily. Okay, on the NVIDIA GPU, we currently, for production, would require LVM compiler, mainly for its very mature OpenMP offload support. We are not very strict on the particular CUDA toolkit versions. We have recommendation because it's more for certain bugs we found in the CUDA toolkit side. But if you can always try the old versions if you don't have the newer versions available, and run the QMCPACK unit test, deterministic test to figure out if it's working reliably. Unfortunately, we don't support NVIDIA HPC compiler because they has certain OpenMP offload feature. It's not missing, but for the particular QMCPACK use case, it's not for supported. So on the AMD side, you can just download the latest ROCm. It ships a LVM compiler. Or you want to use the upstream LVM compiler, it's also possible. But overall, you just download the ROCm and you have everything you need. We recommend 6.3 because of certain issues we find it's only 6.3 release. For Intel GPUs, well, it's also a single kind of installation. You just need to have the OneAPI HPC toolkit available. So it ships you both the compilers and all the MKL libraries with GPU acceleration supported. So just take the release year of 2024 and later. Yeah. So once you kind of get your GPU software toolchain ready, you need to build QMCPACK. Well, I think some people using like pre-built binaries on those established machines, you don't need to go through this, but it's still good to know that how you can even just build one QMCPACK for yourself. It's actually relatively easy. We made changes compared to the past. So historically, we have individual switches to enable CUDA, ROCm, SQL offload, and certain extra flags to control. But we've changed them, we deprecate them from users. You don't see them from your end. They're removed. But since 4.0, we introduced two flags. One is called QMC underscore GPU, which enables QMC features using correspond to specific programming models. And so it doesn't add you new QMC features, but expand the existing QMC features to use the acceleration. So that's the option. Is more for acceleration feature select. It is a semicolon separate list, so you can supply multiples entries, but it doesn't mean all of them work together. You should put all of them. I'm giving you an example. So for NVIDIA, you put OpenMP, and CUDA means OpenMP offload plus CUDA native kernels, that kind of things. So similarly for AMD and Intel, so you change the CUDA into HIP or SQL. The other option we provide you is called QMC GPU arcs. So it is used to select the GPU's architecture, the hardware, which architecture, which generation it has. It is also a semicolon separate list. You can supply multiple entries, but you cannot mix targets from different vendors. But for simplicity, oh, actually I have a typo. The first one, SMXX is for CUDA, the GF for NVIDIA, GFX is for AMD, and Intel GPU is for Intel. It sounds like you have two options, you have many variants, but our recommendation to most users, you only need to specify one entry to the QMC GPU architectures. So when you on a new machine, you just look at what the GPU is and figure out what's the correspondent SM or GFX or Intel GPU, the target name. And once you know that, you supply it to QMC GPU arcs, and then QMCPACK internally will decide the QMC GPU flag for you, for intended for the best acceleration and best performance. So remember, for most users, just set the simplest QMC GPU arcs. Here's some CMake line examples. Very common use case. So on NERSC, you just say SM80. On Frontier, you just say GFX90A. And for Aurora, you just put the PVC. So as I mentioned, just emphasized, put a single entry. The others will be taken care of. However, if you're a very advanced user, you are kind of, okay, I'm debugging certain features, I'm developing features. I don't want all the noise or kind of unknowns from the CUDA. I can specifically just say set additionally QMC GPU equal OpenP. Means it overrides the default CUDA scenario. That means you will have all the calculations done without any CUDA source code or CUDA library. So it's an advanced feature selection for advanced user feature for selecting specific GPU acceleration features. But remember, and let me just remind you again that you don't need it daily. So the other friendly use cases, I personally find it very useful because I'm doing a lot of performance studies, and I may work on machines has multiple generation of GPUs, but I don't want to recompile QMCPACK 3 times, right, for 3 machines. They are all with AMD GPUs. So the simplest way in QMCPACK to do it is you supply 3 entry to the GPU arcs. The limitations, again, it needs to come, all the GPUs need to come from the same vendor. Okay. So actually, I was wondering if there's any questions regarding building QMCPACK.
I don't see any yet, yay. I'll interrupt if I see any pop on the Zoom chat or
Okay,
workshop Slack.
yeah. So now is the second part about how to set up the run. Before starting all the machine related thing, of course, we need to think about whether uh, like all the interactions between QMCPACK input and the code. Uh, in QMCPACK, within the current code, all the GPU flags, there's only how the one name. It's called GPU equals something. So it has a coarse grain selection, yes or no. It has fine grain selection for specific implementations. Actually, for most users, nowadays, if you build a GPU code, actually you should not set this GPU input flag. You should just leave it without setting it. By doing that, QMCPACK will decide the optimal performance implementation for you. I mentioned this tag is mostly for certain scenarios. If you're running an issue and we are helping you to figure things out, we might request you to use this option to turn off the GPU acceleration for a specific component. For example, a adjuster factor. We have a question in the one-body adjuster implementation. We might ask you to set GPU equal no to rule it out. Rule out the possibility that issues from the one-body adjuster GPU acceleration, that kind of scenario. Just let you know it does exist, but again, avoid setting them unless being requested. Okay, now you have the input file and you have the QMCPACK executable. You need to run it. To run it, you need to set, most of the time, the only thing is you need to set the MPI exec or MPI run. That means you are kind of handling the parallelization and you are mapping the QMC calculation onto an actual hardware. So before going that level of detail, I'm gonna just quickly remind you the parallelization in QMCPACK. And there's also one specific things that we introduced in the batch drivers. Nowadays it's default for everyone to use. So we all know QMC calculation involves random walking. Its parallelization is done with all the walkers. Uh, so, however, it has a lot of concurrency, so that's why we parallelize it. But for optimal efficiency, we kind of have a second level of dividing, a second level organization, dividing the whole workers, I call it population, into several crowds in the QMC calculation. So with these crowds, we can maximize the utilization of GPU. So the way we are doing it is all the workers within a crowd will operate in lockstep for maximized kernel efficiency. Different crowds will work totally independent. By doing that, they can kind of time sharing the GPU. When the GPU is not servicing one crowd, it can potentially servicing another crowd. So maximize the utilization of GPUs. So with this design, crowd is important, but in the actual implementation, crowds are mapped into CPU threads. So that's why QMCPACK use CPU threading also on the GPU code. So OpenMP threading is used always in QMCPACK. But if you ask me what's the optimal threads for CPU case, I think everyone knows that is you should use all the cores. But in the scenario of GPUs, CPUs are mainly to handle work to the GPU. So you just need to choose a good number, and empirically we found 4 threads to 8 threads above okay, which is actually in good range with most GPU machines we have today. Uh, so the reason I say 4 to 8 is when you have too few crowds, it if you do need a few crowds to enable asynchronous computation, to enable efficient time sharing and asynchronous computation. However, you cannot have too many crowds because by dividing work into two small chunks, GPU gets inefficient. So that's why just keep them in mind. Roughly, we found it's roughly 4 threads to 8 threads per MPI rank is the best choice. Well, here I mentioned the debug thing. It's not very critical. So just to give you an idea, with different crowds, so on the right side figure, you see different timelines. Every row is a thread. You will see that actually different threads is working on different things, but at the bottom, you see that they kind of share the hardware and keep it busy. So that's how we design the crowds to maximize the performance of the code. And as I mentioned, crowds. So here's to show you that you need to use the crowds to maximize the performance on GPUs. So in QMC calculation, let me first define when we say performance, actually I'm referring to throughput. So the throughput is calculated as the number of samples, which calculated as population by the number of steps and number of blocks over the time. So samples over time. Since I'm doing a performance study, the samples is only determined by the populations and steps and blocks. I fix the steps and blocks, and I just to adjust the population and using the input parameter called workers per rank here. So now on the right side is the throughput benchmark. And you start to increase the workers, you will see that the throughput gradually increase, increase rapidly from the beginning and then saturate. Because when it saturates, the bottleneck is your computing device. Your GPU is saturated, it cannot handle more computation, it doesn't gain your throughput. But the red and the blue line, the difference is the red line has only one crowd, means it's not leveraging the asynchronous computing, while the blue line has 7 crowds. That means that the computation is time sharing and try to squeeze every bit of computation that the GPU can do. You can see that at the peak performance area, the saturated area, you will gain with a bit more crowds. If you are not using the crowds, you are not using the threads, you will lose the performance. Okay, so in practice, I said 4 to 8 threads, 4 to 8 that translate to 4 to 8 crowds is a safe bet in most GPU runs. And I'm showing you this worker scan, and I recommend everyone doing it. When you run like 1,000 similar calculations, first, before doing that, just fine-tuning the performance of your run by scanning the workers, have a similar figure, have an idea how the performance is, then set the parameters in the following 1,000 production runs accordingly. Okay, so Paul mentioned that we can use the workers per rank to calculate, setting the population. Also, the total workers can be used to set the populations. These two parameters is one-to-one mapping. Like if you set one, the other one will be determined. Just remind you in case these two, I think total workers are more convenient per se. When you set it, the total workload of the calculation is fixed. However, you also need to pay attention to the corresponding workers per rank if you are running into a memory constraint scenario, or you are deciding the performance, because workers per rank is more directly connected to the memory consumptions, and we all know that GPU memory is a constraint, is a limited resource. just remind you that when you're doing a GPU run, set the workers per rank or set the total workers. You need at least of them, and you need to think about why I'm setting these workers per rank, because you need good performance on the GPU. Okay. Okay, I've explained that QMCPACK relies on the crowds and threading. So now we need to decide how to set up the run for, that is the MPI run or MPI exact in our simulations. For GPUs, first thing first, decide the number of MPI ranks per node, because because QMCPACK works best with one GPU per MPI rank. Dedicate one GPU to each MPI rank. So the number of MPI ranks is exactly the number of GPUs. Once the number of, you know the number of MPI ranks, you need to just fission the CPUs on the node, basically divided all the number of cores by the number of GPUs. And with that number, you need to carefully set, making sure affinity are correctly set. So making sure if you have four MPI ranks, each of them, all the cores living within the same NUMA node. Second, the last thing is, people were wondering about hyperthreads. I would say just don't use them. If you're just getting on a new machine, just don't use them. Most of the time, it's not going to be relevant, because in most of the GPU machines, we found that we have even more CPU cores than actually needed for getting the GPU busy. Okay. So on the right side, I'm showing you how you do the math. On Perlmutter, it has 64 cores per node with 4 A100 GPUs. And as I mentioned, the number of GPUs is 4. The task per node is 4. Then you divide 64, because don't do this hyperthread. You only have 64 cores. Divide 64 by 4, and you get a 16. So each MPI task will has its own dedicated 16 CPU cores. And I found it friendly, how to say, not friendly, find it useful. You always kind of specify this option, explicitly telling MPI, I need one dedicated GPU per MPI task, just specify equal 1. Similarly, on the Frontier machine, because Frontier, even it has 4 GPUs, but you have to treat each GPU as 2. That's why it's 8 GCDs. And so you set a number of tasks per node equal to 8. And if you carefully read this menu, the user guide, it says that there are 8 cores being reserved for the operating system or runtime specific needs. That's why actually there are only 56 available to use, and you divide by 8, and the CPUs per task is 7. So you set GPUs per task and set the binding, say, okay, each MPI find its nearest GPU. Okay, now you have the MPI exact run that line written, right? So remember, MPI exact, MPI run is to how you allocate the resource to QMCPACK. The second stage is how you QMCPACK use the allocated resource, right? One is you from the node, you use MPI exact, MPI run, allocate the resource to each QMCPACK MPI task. The second step is, well, each MPI task now is being assigned a few cores and a GPU, how we consume it. So in this aspect, there's not much we really need to care about. So the only thing is the OpenMP part, because I said we assigned a bunch of cores to each MPI rank. We need to set up how QMCPACK use them for threading. One control is OMP num threads. The only requirement is it needs to be equal or smaller than the CPUs per MPI task. That's why on the right side, you see the per example. Earlier, I mentioned 16 cores be assigned to QMCPACK. But because QMCPACK doesn't really need to use all of them, you can explicit set export on pnum threads equal to 4. Say, oh, I'm only using 4 of the 16 cores. Okay. So there are additional OpenMP flags. Most of the time, you don't really need to set the bindings affinities because usually it's kind of well handled by default. Yeah, similarly on the I'm also showing you Frontier. So there are 7 CPU cores assigned to each MPI task. So by default, we give you on pnum threads to 7. And just use my empirical 4 to 8. I usually just leave it. I don't need to set it to 7. By default, it's 7. It's good enough. Okay. So the real, I think users find its setting affinity is relatively easy on AMD machines because the number of cores usually is exactly multiple of the number of GPUs. But unfortunately, it's not the case in the Aurora machine at Argonne. On the Aurora machine, you have 2 sockets, and each socket CPU has 52 cores. That means, but it has 6 GPUs. To some degree, it's like AMD, you actually need to use 12 MPR ranks to eliminate certain NUMA effect. So remember, we have 2, now we actually have like 12 MPR ranks, and we have 52 cores by 2 sockets. So it's not really divisible. So how we gonna do it? So the solution is we gonna actually only use 48 cores on each socket. As I mentioned, there are more cores. You don't, QMCPACK doesn't need to use all of them as long as you are running on its GPU. So in the Aurora case, I always said there are 12 ranks per MPI, and because 52 for how to say 52 by 2 is 104, then there are 12 GPUs. So roughly at maximum on average, not on average, maximum you can guarantee 8 cores per MPI rank. However, because the 48 for the first 48 lands on the first socket and second 48 needs to be on the second socket, you need to explicitly give the binding details. So I'm here giving you the actually binding list I'm using, and just to let you know that you can provide this kind of control in with MPI, and in certain scenario like Aurora, you should do it. So in this list, I'm highlighting the cores actually doesn't. If the core enumeration starts from 0, but if you read carefully on the Aurora user guide, the core 0 is reserved for operating system. You won't get it through MPI exact. That's why I need to start from 1. So 1 to 8, 9 to 16, and up to 41 to 48. So that's on the first socket. And I leave a few empty, I skip a few cores and start from the second socket. So in total, there are like 12 groups. So correspond to the 12 MPI ranks I use. So that's the way how you divide the resource on a Aurora node and map them to QMCPACK runs. For GPU in QMCPACK, on Aurora for GPU assignment, GPU affinity, there's a script provided. The GPU tile compact will assign each MPI rank to its own dedicated GPU. So its effect is similar to the previous GPUs per task equal 1 in the Slurm options. So you just need to remember, set the affinity of CPU core, set the affinity of GPU, correct, making sure you get the best performance. Because if you mess up those fine details, my experience shows you're not gonna get a speed of how to say, it's not like 50% performance loss. You can potentially get only 1% of performance of the actual performance you should get. Okay, last part, I'm going to, so mention about the memory usage of QMCPACK. Memory is your simulation confined by the on-node memory in two portions, the CPU memory and the GPU memory. When you are not sure how much memory is being consumed, you can look at the output of QMCPACK. We print out those details in a few locations from the very beginning of the run, so you know that how much memory is available when the simulation starts. But simulation start means like no QMCPACK specific settings being activated. It's only like a vanilla, more like MPI hello world situation, how the memory is being consumed. Then later, after all the initialization is completed, we print out the memory. Then also during the BMC, DMC driver runs, we print out memory in a few locations. Like for example, after warm up, here it prints out the actual memory. I'm picking out after warm up time frame is because it's roughly the highest watermark of the memory footprint used by QMCPACK. Because the highest consumption situation matters, right? That's how many workers you can squeeze in or how much kind of efficiency you can gain. So you can look at the details. First line is it says available memory on node 0. It's specifically calling out node 0. So it's not rank 0. Node 0 means the available free memory available free memory on the node. This is shared by all the MPI ranks within node 0. Second is the memory footprint of rank 0. That's also a CPU memory. So you can figure out, okay, because in QMCPACK every rank mostly have the same memory consumption. So you just need to figure out how many CPU memory you're actually using. You can multiply this number by 12 in the case of Aurora. Then later 3 lines, we are calling out device memory. And if you remember, we are assigning one device, one GPU per each MPI rank. That means this memory is technically, in most scenarios, as long as you're not oversubscribing GPUs, it's the memory per MPI rank. It's per GPU, but it's also per MPI rank. So based on how much being allocated, how much being available, you can decide how many further workers you can add if it's needed, right? So these are the memory reports you should look at if you run into memory issues. And a few more memory considerations for QMCPACK runs. For best performance, we made choices to keep data on the GPU memory. One of the large portion is the B-spline table. We leave it on the GPU, keep it GPU resident. And this is shared by all the workers. So when it's a one-time cost you have to pay, a fixed cost you needed. Then the other parts of calculation, for example, the determinants, they are kind of per worker. That's why they scale linearly to the number of workers. And in extremely large simple problem sizes, you may not be able to push more workers to further gain performance. In that worker scan, you might get stopped at a small amount of workers because that might be caused by memory constraints, the GPU memory constraints. So in that scenario, you can, for example, then use some ways to work around it. For example, by default, matrix inversion is done on GPU. In that scenario, if you think you're not doing matrix inversion that often, you can turn it off, say do the inversion on the host. That means you give more memory you don't need to use the scratch memory for all the matrix inversions, and you can assign those memory to having more workers. So yeah, and another example is you can just turn off the particle set GPU feature to no, turn it off, and all the distance table will stay on the CPU. So will not consume GPU memory. And the other possibility is you can use hybrid basis set to reduce spline memory consumption. So these are your options to kind of getting more memory on the GPU. Okay, that's or what I wanted to share with our users regarding GPU. So we have very good GPU feature support across all the vendors. They are very easy to enable. Just for users, when you're running your simulation, pay extra attention to how you should set up the CPU core affinity and GPU core affinity. Otherwise, you're gonna badly mess up your the code performance. Also, it's recommended you have a quick worker scan study on a single node for the simulation that you're gonna run 1,000 times. And do this quick scan, figure out optimal worker counts. Of course, optimal is kind of subjective because you need to make a choice between the how close how close the performance you want compared to the peak throughput, and you might need to compromise it regarding the time to solution. You probably want to finish your simulation sooner, so you may not aim at maximum efficiency. I would say most of simulations, if you're at the 70% of you're above 80% of the maximum throughput you measured, you're typically fine. Okay, that's all what I have.
Thank you, Yi. So the talk is open for questions. And I do see one, but I will stall for a moment with a comment to allow people to add more. And the comment is for anyone who's not used to running on GPU machines, but might be in future. I think Yi's explanation of thinking about the resources you're going to run on and how to allocate them is going to apply to not just QMC, but more or less any run. That's a little planning step you should go through.
Yeah.
So there was one question about SPAC, which has been answered. And there's a question from Paul Yang on Zoom that I'll read out, which is, what's the downside of setting OMP num threads equals 16 on Perlmutter? Is it just that it creates too many crowds? Would 8 be okay? So what's the logic around setting the number of threads on a machine like Perlmutter, which has got 4 A100s from NVIDIA, if I remember correctly?
Yeah, so if you set, so because the number of crowds by default would taken as the number of OMP num threads. So when you have 16 crowds, usually you're gonna compromise a bit. The kernel, each kernel will has fewer workers. That ends up you compromising the efficiency of individual kernels. So you are paying a bit more on the overhead, GPU overhead, I would say. So this is a performance argument. Actually, I think the second argument is actually memory, because we are intent to have them run independently. That means we are spawning per crowd some resources. For example, a cuBLAS handle, a cuSolver handle. Those library, each handle, like a library instance you create, it takes away, I think, at least 100 megabytes per instance per handle, up to like 400, 500 megabytes per handle. So it's not a light amount of memory taken away from you. That's the second argument. That's why for both reasons, it's not really necessary to go beyond 8. That's my experience.
Thanks, Yi. We've gained a couple of other questions, and I might chip in with my own view on a couple of these. The first one here, or the next one is, considering the price tag on modern GPUs, is it competitive with a CPU-only simulation with respect to dollar per result? Excellent question.
Well, it depends on what kind of dollars you're talking about. I would say uh, if you're using a resource provided by others, probably the dollar argument is not what something user really need to think about. But if you are talking about you are setting up your own cluster or you have a workstation, the money can be justified, to be honest. So in that scenario, I would highly recommend you just buy the cheap GPU, gaming GPU with a decent amount of VRAM, and I found it's a good investment, I would say. So that's the reason why QMCPACK, I mentioned earlier, we support all kinds of GPUs. We kind of allow you to make a choice for your need.
Thanks, Yi. Yeah, I would add essentially what you're applying, right? If you're going to be buying something, definitely do your own benchmark for your calculation with respect to what you can buy. Certainly the prices of GPUs can be quite high, but the more consumer ones are lower. And if you're only looking to build a sort of a small cluster for yourself, that might be a good route to go. I know quite a few people at universities have done that. The next question, when you said that OMP num threads must be less than or equal to CPU per MPI task, what is optimal?
So okay. In case of if you run QMCPACK in the past on CPU-only machine, the optimal scenario is equal. So in the scenario of GPU runs, if the number is higher, like SPERMA to 16, I recommend you explicitly lower it to 4 to 8. That's just an empirical choice.
Thanks, Yi. So quick final comment from me before handing back to Yi in case he's got a final word. My general comment for all of this would be if you're just running one calculation, just pick something reasonable that you know works from experience, or just do a little initial test. But it's only when you come to do like 1,000 calculations, as you were saying, that it's then it's really worth spending the time doing that Walker scan, for example, to squeeze out that extra performance. Final comments, Yi?
Yeah. Okay. Yeah. How to select? I'm thinking of how to select a good number of workers per rank. If I would say most users you just try like 1,000 to 2,000. That's a fairly good number. The reason is 1,000 is kind of ballpark match is more like 10 times of the, you can call it GPU cores, or on NVIDIA it's called SMs, roughly that number. So that's why I recommend if you just want to start your running, not heroic simulations demanding a lot of GPU memory. For small runs, just set 1,000, roughly 1,000 is a good option, a good default, good value.